Hi, I'm Randall Heyman, a mathematics academic. Welcome to my Corona Help playlists, where I do quick turnaround videos to help educators and their students. If you'd like me to make a video for you, be it at primary school, secondary school, or university level, then comment me below any of my videos or drop me an email. In the previous video, I went through open and closed sets, and I gave a couple of what I'd regard as simple examples. Wanted to do a couple now that are actually not that much harder, but they'll just illustrate a few things. I'm actually getting these from a book by, that's right, yeah, Real Analysis. It's a book called Real Analysis by Frank Morgan. But, you know, I won't get all the problems always from that. And just in this case, I think they're quite okay. Otherwise, I'll use other books or stuff online to get some questions, or in some cases, I just make them up. Often I just make them up. Okay, which of the following are open, closed, both, or neither? Okay, A, 0, 1, like that. So draw the real number line. We include the point 0. 0. We go up to 1, but we don't include the point 1. So I'll draw it open like that, open circle, and it includes all of that. Should do it in another color, shouldn't I? Okay, well, is this open? Is this open? Well, if it's open, it can't contain any of its boundary points, but here's a boundary point. That's a boundary point. Why is that a boundary point? Because if I draw a little ball around it, it contains some of the set and some of the outside the set. So that is a boundary point. And if it's going to be open, it can't contain any of its boundary points. So it's definitely not open. So let's write that out there, not open. Is it closed? If it's closed, it's got to contain all of its boundary points. Here's a boundary point that's not part of the set. So I'll say that again. This is a boundary point. You could draw a little circle around it like I did previously. And you'd come to the conclusion it's a boundary point. Because it's a boundary point, in this case, it's not part of the set. And a closed set has to contain all its boundary points. So this is not closed. Is it both? It's clearly not both. So I think we come to the conclusion that it's neither. It's neither open nor closed. Okay, what about this one? The integers in the set of reals. Okay. So how does this look? Let's draw a proper real line. Okay. So we've got the point 0, the point 1, the point 2, point -1, point -2. Okay, so let's think about this set. So I could just take any of these. The conclusion is going to be the same. So here's the set. Here's in respect of the point 1, the integer 1. I draw a circle around and I say, well, part of that ball is in the set. So what am I saying? I'm saying 1 is in the ball. So this is the ball around 1 of radius, I don't know, 1/10. But if I look at the point 1 and 1/20th, so that's 1 and 1/20th. So it's 21 on, no, what is it, 1 and 1/20th? I'll just write it like that then. 1 and 1/20. Yeah, 21 over 20 is not part of, well, 1 is part of the ball and 1 is an element of the set Z. But 1 and 1/20, it is in the ball, but it's not part of the integers. So this is a boundary point. So 1 is a boundary point. And in fact, so let's now write, every element of Z is a boundary point. And to go a little bit further, I suppose, we could say Z contains all of its boundary points. So Z is a closed set. So this is now starting to get a little bit well, not counterintuitive, but a little bit more difficult. C, actually C is pretty easy. I won't do C. Let's do D. The union from n equals 2 to infinity of the set 1 over n to 1. But notice the brackets have to be nuanced about that. The square bracket means we include 1 on n. The round bracket means we don't include 1. So let's draw the real number line. So let's call this point the point 0, and this can be the point 1. So if we've got n equals 2, what do we get? We get a half 1. So I'll sketch that in. Why don't I sketch that in? A half 1. Yeah, that's right, a half 1. It includes a half. So I might actually write it on top of it so we can stack them up. That might be a bit easier. So let's just do it like this. What we'll do is we'll draw that as, we'll say that's a half. And then I'll draw it here above it. A half to 1. Okay. N equals 3, 1/3 1. So let's now draw a third is about there. Okay, and we get, let's do n equals 100. I mean, obviously you've got to do all of them. It's a union of all of these, but I just want to illustrate. I'm trying to just illustrate what's going on here. So for that, we'd go to here, which is 1/100th, and we draw that in. So what we can see happening here is that the union of n equals 2 to infinity of 1 on n slash 1, 1 on n, comma 1, what is that equal to? Well, it actually ends up being 0 to 1. We get closer and closer to 0, but we never get to 0. Okay, and this is an open set. So this is a case. This is a case where you take an infinite union of sets that are neither closed nor open, and the result is an open set. Okay, that's all I wanted to say about open and closed sets. In the next video, unless I get questions before I do it, I'm going to look at continuous functions, which sounds like something that's got nothing to do with open and closed sets, but it's an incredibly important idea of linking continuity being linked to the standard definition of that we see in continuity for a function versus continuity with sequences versus open sets. If you've got any questions on what I've done today, open and closed sets, then please feel free to comment me or email me. And the same applies with anything in mathematics. If you think I can help you, then please contact me.